Astronomy Cast, episode 276 for Monday, October 15th, 2012. XMM-Newton. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. I just went on a road trip, and I wanted to share something with people, which is if you've never done this, you should absolutely do this. Now, I live on Vancouver Island, so we often go to the United States, down to Seattle. And when I was in Seattle, we just, like, on a whim, went to the Boeing factory, and it is a phenomenal place. It is amazing. It's it's the largest building in the world by volume. They kept telling us this, but you get to see these planes being built, and it felt a bit like I was watching spacecraft get built. You can see 747s getting built and the way they crane them around and stuff. So if you're ever in the Seattle area, and if you live in the Seattle area and you haven't been to the Boeing factory, shame on you. Go check it out. It's awesome. There you go. That's news you can use. What have you ever seen? Like, you've actually seen rockets launch and rockets constructed, right? So.
Yeah, so I've got to go tour around Johnson Space Flight Center where they were working on constructing space planes at the time. I've been down to Kennedy and seen Grail launch and seen the shuttle launch. But no, I've never been inside one of the Boeing factories, and so that sounds mighty awesome. So
yeah, it's super cool. So let's get cracking then. So on the plus side, the Earth's atmosphere keeps us alive, and on the downside, though, it blocks X-ray radiation from reaching the surface. Okay, so maybe that's still in the plus category. Still, in order to understand the universe at the higher energy levels, you need to launch a space telescope, like the European Space Agency's XMM-Newton telescope. So let's learn about the telescope, named for the famous scientist. All right, so cool. So let's learn about the telescope. Now, what's the history of the telescope? When did the ESA decide they were going to build themselves an X-ray telescope?
Well, the plans for this one started in the early 80s. It got built in the late 90s, started doing science in 2000. And this is the mission that just refuses to die. So it's been going since 2000, which admittedly means it is younger than the Hubble Space Telescope and several others. But it's had its mission extended a number of different times because it's still doing very good science. It's still a workhorse. And one of my favorite random mission statistics is this satellite, because it observes in the X-ray, it has to get very distant from the Earth. It has to get out far enough that it's beyond the Earth's radiation belts. And so it actually has a 48-hour orbit that brings it down fairly close to the Earth, then whips it out into this nice slow orbit when it's furthest from the Earth. And so it's had, as of the day that we're recording this, 2,357 revolutions around the Earth, and it's had 3,190 refereed papers that used its data. So it's actually producing papers at a rate that, on average, is greater than its orbital velocity. Well, not velocity, but orbital rate.
Yeah, and it's funny because as the publisher of Universe Today since 1999.
Yeah.
One of the first stories that I worked on was the launch of the XMM-Newton, and have been sort of reporting stories from that just nonstop for 12 years now.
Yeah, and
it's a funny thing. I mean, it's going, and it's doing, it's gathering tons of X-ray radiation, and many of the pictures that people have seen out there were taken by this spacecraft. They don't realize, it's it and Chandra are really doing the heavy lifting out there.
And it also has one of the illustrators that we end up seeing their work over and over and over. So if you've ever seen any of these gamma ray burst animations where you see the beautiful many reds and creams disc with the jets jetting
black
out,
holes, and
a lot of these are pieces of art that were originally commissioned to go with the XMM-Newton, not to be confused with the radio station, XMM-Newton spacecraft. So there's lots of little ways that this hard to pronounce spacecraft has snuck into our understanding of astronomy.
Now let's go back to a bit for a second here. You know, why do we need to have a space telescope for X-ray radiation, and why is that important?
Well, so the why do we need it boils down strictly to our atmosphere is kind enough to block high energy radiation from reaching the surface of the Earth, so we don't get X-rays, we don't get gamma rays. Superman's X-ray vision is always perplexing because in order for X-ray vision to actually work, you'd need the X-rays to be coming through the person, but there's no source of X-rays. So yeah, unless he's doing backscattered X-ray like they do at the airports, Superman's X-ray vision just doesn't, it's missing a few scientific details there.
He would be emitting lethal doses of X-ray radiation in all directions and then looking for the backscatter coming back, right?
Yes, yeah. So Superman, it's one of those Marvel fails. But so without the X-ray and other
before you
high...
get in trouble, before you get in trouble, it's DC.
Was it DC?
Yeah,
oh,
yeah.
Sorry.
Don't send an email, please. But anyway, continue.
Sorry, I goofed.
But what do we use this X-ray radiation for? Like, what will astronomers want to use it for?
Well, it's so different colors map to different temperatures of processes going on throughout the universe. Really, really hot processes, very, very high energy processes, end up producing high energy light, high energy photons that we end up detecting in the X-ray. So when we see the shock waves of exploding stars compressing surrounding gas, those shocks can emit X-rays. When we look into the hearts of galaxy clusters where gravity is compressing all of the intercluster material, we see X-rays getting emitted. So there's a whole variety of different processes ranging from explosions to extremely dense environments that all end up releasing X-rays. And we can't understand those processes if we can't see those processes. So by launching these space telescopes, we're able to tap into part of the data that we can't see from the surface of the Earth and build a more spectrally varied picture of our universe.
Right, okay, and so it's sort of like certain kinds of processes in the universe are going to give off this X-ray radiation, and that can then tell you that certain things are happening, like
and a good way to think
clusters, and yeah.
A good way to think of this is here on Earth, imagine if suddenly you couldn't see anything that was yellow, orange, or red. Just suddenly all of that information is gone. There's lots of things that suddenly would be harder to understand. Well, there's lots of colors in astronomy. Yeah, so
yeah.
There's lots of colors in astronomy that we can't generally see. Certain bands in the infrared that don't make it through our atmosphere, certain bands in the radio that there's just too much molecular stuff in the atmosphere. But then all the high energy stuff gets blocked, and so we're trying to build a data-based understanding of our universe, so we need all the data, and that includes all the X-rays.
And so, okay, so let's talk about the observatory itself again. So, I mean, you mentioned it was launched in 1999. How was it launched?
It was a regular everyday rocket, one of the Ariane 5 rockets, so nothing exciting about how it was launched. No space shuttle missions were involved. This is a European mission.
Right, but they probably launched it from their South American
They did.
facility,
They launched
right?
it from French Guiana.
Yeah.
And if you've never watched any of the videos or seen a launch down there, one of the awesome things about the videos, and I'm guessing if you're there in person you see this too, is there are giant birds on this island.
Right.
And so as you're watching the launch, it looks like occasionally like a pterodactyl has just flown through the image.
You see that a bit in Florida too, though. You know, great big birds flying past, but yeah.
Yeah, I missed them there, but so this is a great facility, and one of the reasons that it's such a great facility is it's close to the equator, so you get the extra velocity from the Earth's orbital rotation. It was launched into an extremely elliptical orbit. As I said earlier, it actually gets to about a third the distance to the moon at its furthest away. Nearest, it's still many, many times further away than the International Space Station. Its close point is still 7,000 miles up.
Now,
So,
you mentioned, sorry, that it's trying to avoid the radiation belts. Is that right? Or
well, it's
it's
trying to get out of them for the majority of its orbit. So it spends about 8 hours of its 48-hour orbit inside the radiation belts, which gets it closer, and it's easier to transmit data back down to the Earth. That's not the primary reason to do this. But the advantage of having this highly elliptical orbit is one of the things that Kepler figured out is when you're close to your thing that you're orbiting, the sun, the planet, whatever it is that you're orbiting, you move much faster than when you're further away. This is the equal area and equal time part of the planetary laws. And with this highly elliptical orbit, it spends 8 hours whipping past the Earth, going through the Earth's shadow, but then it lingers for long periods of time much further away, and it can get 10, 12 straight hours on one source without any difficulty. Now compare that to other objects, other spacecraft that are orbiting every hour and a half or so around the planet. They're constantly getting a changing view. So with this longer period orbit, you can get longer observations. X-rays are a bear to detect. Objects that are giving them off aren't giving off a lot of them most of the time. So you're able to get long period exposures and count each of those little individual photons that are coming into the telescopes.
And so the other sort of main telescope for this is the Chandra X-ray Observatory. So how do they compare and contrast as two observatories? I mean,
well, so XMM-Newton, it has 3 different major instruments, and it was designed originally to do spectroscopy, to measure what are the wavelengths of the different photons that are coming in and hitting it. So it's trying to figure out what sorts of oxygen and iron heavily ionized systems are out there, and it's specially designed. In fact, its original name tied into its spectral capabilities. It's designed to go out and count the photons coming in at the specific wavelengths, allowing it to. It's hard to explain if you're not a spectroscopist why this is cool. So the way to think about it is, sorry, I just hit this wall of I don't know how to make counting ionized photons cool.
well, I mean, cooler than it already is. I mean, it's
Right.
inherently a very cool thing, but I mean, specifically as it relates to this telescope. No, I understand.
Yeah, so there's basically gas out there that you can measure its composition, you can measure its temperature, you can measure all sorts of cool things just by knowing the iron is doing this, the oxygen is doing this, the background continuum is this. And you get this through spectroscopy. We've done episodes on spectroscopy before. There's no easier way to make people's eyes glaze over than to show them spectra.
Light stuff on fire, you can figure out what it's made of.
Exactly, and the universe conveniently sets itself, well, not on fire, but ionizes itself, which causes
does various
side
things
effects
to itself. Yeah, exactly. And then that tells you what it's made of. As it's destroying itself, you can tell what it's made of. So that's perfect.
Yeah. So one of the other side things that XMM-Newton has that makes it novel in some ways for the time that it was built, this has been repeated since then, is it actually had an optical imager on board as well. So it was possible for it to monitor in optical and ultraviolet wavelengths where it was pointed, and
Right.
to start to match the X-ray sky and the optical sky. One of the things that we really struggle with in astronomy is how do we align all these different wavelength maps? Day-to-day life, we look for a signpost and we say this signpost is the corner of Main Street and St. Louis Street. I live near that corner. But when you look out at the cosmos, you don't have signposts that necessarily give off light across the entire electromagnetic spectrum. So you can say, well, here's a signpost I can see in the optical. Here's a signpost I can see in the X-ray, are those the same signpost? And so being able to take simultaneous observations, it helps. And over time, we're working to try and find more and more signposts that we can use to unify our maps.
And there's a lot of really great images that come out, both from from NASA and also from the European Space Agency, where they do these combined photographs where they use like blue for X-ray, red for infrared, some other color, for visible, and then they merge them together so you can see, these are the parts that are the dust that's, the warm dust or the cool dust, and then these are the parts that are giving off X-ray radiation. It's by seeing all those things all at the same time that you can really get a sense of what's going on in the picture. So I know for scientists, they want to do that all the time. They want to look at the same thing in as many different wavelengths at the same time, because each of those wavelengths is telling a story, and by putting them all together, you get the full story.
Yeah, and some of the pictures, Centaurus A is one of the ones that I think gets abused in multiple wavelengths the most often. Andromeda is another one, but Centaurus A, it's a system that's gone through recent interaction. So when you look at it in the visible, you see this really mutant dust lane cutting through a big elliptical core. And as you look across multiple wavelengths of it, you start to see, wow, this thing in Herschel's images, you see this beautiful disk bent through the system. So there you're starting to pick up the far infrared. As you look at it in the X-rays, you see this core is giving off a jet, and there's bubbles of shock waves interacting with the materials, and so you're getting different physics out of these different colors, where in the infrared you see the warm dust, in the X-ray you see the shock waves and the jets, and it's through putting all of these different pictures together that we're able to understand all of the different science that's going on in this recently interacting system of this active galactic nuclei.
Yeah. Now you do you know sort of what the capabilities are compared to Chandra? I mean, do they use one instrument for a certain kind of work and a different one for a different kind of work?
Well, so both of them have similar scattering mirrors. So the way these types of telescopes work is, in order to collect photons, you use grazing mirrors. So it's not like a single mirror like you see in the visible. Instead, you essentially have a cone of mirrors that scatter the X-rays down onto your detector. With XMM-Newton, they actually have two different telescopes side by side for collecting the X-rays. Each that have their own instrument. Where you see the biggest difference between the two systems is Chandra does have greater sensitivity. They also have very different orbits, which allows them to take different types of observations.
But if you were a scientist, or if you were a scientist and you were going to work on some part of X-ray radiation, would you submit for time on both devices, and then if you got one, you'd be fine with it?
No, you do use them for slightly different things.
Right.
So just like there's times when you need that 1-degree field of view that you can get off of a Schmidt telescope that has a 30-inch mirror, and you can do some great survey work. There's other times when you need that 10-meter mirror and a 1-minute field of view. So the two telescopes have different sensitivities. They see slightly different parts of the X-ray spectrum. XMM-Newton's a little bit easier to get time on. Chandra's more competitive. It's a slightly more sensitive telescope, or somewhat more sensitive telescope. They just have different purposes.
Right, okay. So now, do you know what the original lifespan was supposed to be for this telescope? Like as we said, it's one of those just keeps going and going.
It just keeps getting extended and extended and extended. It was, I want to say that they were originally planning to have it go only into the early 2000s. It's currently extended, they're in the process of reviewing it in 2012, but it's looking like it's going to keep going probably till 2015. They were thinking that it probably has enough fuel on board and all of the stuff that you need to keep it pointing, keep it going. They think that the spacecraft has the ability to keep going potentially as far as 2018. So this is one of those great things where you build a telescope planning for it to last for a few years that you have the budget for, but you engineer it to last as long as possible, and you keep using it to get science as long as possible.
But this is different from some of the other telescopes out there. Like I know with Spitzer, they had only so much coolant, and they knew pretty much down to the day when they were going to run out of coolant for the cold operations, and then they moved to the warm operations, right?
Well, so the nice thing about X-rays is because they're already high energy photons, it's not like you really need to cool anything.
Right,
When,
right.
when you're looking in the infrared, when you're looking in these wavelengths that correspond to nice warm surface, you have to worry about your nice warm instrument generating the color of light that you're trying to detect from the outer parts of our solar system, of our galaxy, of our universe. So you have to cool your entire system down so it's not generating light that creates background noise in all of your images. Imagine if inside your camera were little lights that were shining on your camera detector at the same time that you're trying to take a picture of the outside world. With X-rays, if the telescope is hot enough that it's generating its own X-rays, you probably don't want to be using it.
Yeah, the temperature of a telescope doesn't matter for catching bullets in it.
Right,
You know,
right.
they're just
And so
they
you
are
don't have to worry
very
about cooling at all. So these issues that affect Spitzer don't affect X-ray telescopes. So it's strictly the types of problems of, well, we've seen with Hubble. Hubble periodically loses gyroscopes and it can't point as effectively.
right.
You
Yeah,
have to worry about how long can the system keep pointing. We've seen past missions, Fuse was one of them, where NASA kept hacking new ways to keep the spacecraft pointed.
yeah. They
And
figure out
so,
it's quite amazing. They're like, oh, we thought we needed three gyroscopes. We figured out how to do with two, and then oh no, we figured out how to do with one,
yeah.
and it's just like really clever.
So this mission seems to be going fine as long as they keep getting renewal to keep listening to it and keep steering it and operating it. I just, like I said at the beginning of the show, I love the fact that the number of refereed papers is greater than the number of revolutions around the planet.
Right. And then, you've talked about the lifetime. So is there a sort of potential successor out there? Do you know sort of, I mean, either from NASA or from the European Space Agency?
I think given the current budget climate
Yeah.
around the planet, it's are there scientists who have plans for potential successors who, if budgets are released, can step in and suddenly have great things ready to go? Yes. I know there's a group of people working on instrumentation for X-rays at Harvard, for instance. That said, there aren't any new, big, giant, awesome X-ray missions planned for the future to supplant XMM-Newton and Chandra.
What would they do if they did? I mean, I'm trying to think. Would it just be
Well, so you can
a
go in
bigger
two different
version of the
directions.
instrument, or yeah?
Well, the two different problems that we have with X-rays are, one, they're hard to detect. So being able to increase the sensitivity, see fainter and fainter X-rays, that's one direction to go in. The other is the suckers are hard to focus. So these are the individual X-ray photons. And some of the things that they've been working very hard on in the past few years is how do you build detectors that have greater and greater resolution so that you can see, well, what are the details of the jets? What are the details of the shocks? So we have the potential moving into the future to both increase the resolution and increase the light gathering capability, and to basically see fainter, higher resolution objects out in the not so distant stars with jets and in the very distant galaxies with jets.
And what would be a sort of future objective that maybe astronomers are hoping for? Because I know, like you remember when I'm trying to remember.
Well,
Was
when
it
Hubble went
Spitzer?
up,
Well,
it
yeah,
had the definitive goals of we want to figure out what the heck is up with these planetary nebulae that have funky shapes.
and how
And we
fast
want
is the
to,
universe expanding?
and the Hubble constant. Those were the two big things. In X-rays, we're constantly getting surprised at all the different things that we're finding. So we're discovering magnetic stars that give off X-rays when their magnetic fields rearrange. We're discovering fast-moving pulsars, in some cases perhaps shot off during supernova explosions. We're discovering one of my favorite more recent results was in the spring. It was found that the supermassive black hole in our own galaxy, it periodically essentially burps X-rays. And these X-rays have reflected off of ionized atoms. And we can map the location of that ionized gas by looking at the differences in how we're seeing the light come back to us as it gets reflected from this echo. So just like you can in some ways map out a room from the way the sound echoes, we find that we're able to map out the cores of galaxies based on how the X-rays echo through the cores of galaxies.
That would be really cool.
And it's not a will, it's an is, and our ability to do this will only increase as our technology increases in the future.
Right, right. Very cool. Okay, well, so I guess we need more funding.
Yes, always.
More funding, please. Yeah, always. All right, well, cool. Well, thanks a lot, Pamela. That was great, and we will see you next week.
Sounds good. My pleasure. Okay, saving.
Also saving. So a couple of people mentioned that I said that it was October 15th. So if you notice, we actually missed a week. So we're making up last week. And then we're also going to probably record another episode within the next couple of days to catch up this week. You were, I believe, in some kind of airplane hell last week.
Yeah, so for those of you who don't know, American Airlines is having problems with pilot slowdowns right now. Which means that if there's anything potentially that they can complain about on your plane, they will. And this has led to all manner of Pamela running in heels through O'Hare. Now, admittedly, American Airlines has saved my butt a few times by changing the gates I was landing at and other rebooking me on flights. And it was just one of these things, though, where I got home after we should have already been recording and really just wanted to sleep.
Yeah. Yep. Okay, cool. All right, so I've saved. You've saved?
Yes.
All right. We're safe.
We are.
For how long? Right, okay, so as I mentioned, top of the show, we're happy to take some questions and comments in any astronomy-related things you want to know. We're happy to take a crack at them. So there's a few comments came in. Detlef Crows had a bunch of great comments while we were recording. He mentioned that the XMM's perigee is 7,000 kilometers, not miles. So,
oh, crud.
Yeah, maybe at some point Preston can edit it where you go like 7,000 kilometers. Edit afterwards. And then Detlef also is mentioning that Athena was a candidate for L1, but JUICE was chosen instead. Do you understand what he's saying there?
Yeah, those are two different missions that were finalists for funding, and Athena detected X-rays. I forget what JUICE was looking at. I am guilty of not following or believing that missions exist until they launch, with the exception of the James Webb Space Telescope, because really all of our funding is going to it. If it doesn't launch, we all cry.
Yeah. Let's see. Anyone else? Okay, so Sean Coleman is asking, is Cassini using X-rays on Titan, and if so, is it the same type, or has science refined the spectrum?
I don't know if Cassini has an X-ray detector. I know that Chandra has detected X-ray aurora at Saturn, and this is me Googling, has detected X-rays from aurora at both Saturn and Jupiter. I don't know if Cassini has an X-ray detector. And there's also a distance issue sometimes. If you're too close, you just don't see things as well. It's sort of like the dust storms on Mars are in many ways best observed by amateurs here on Earth.
Greek Person 0305 on YouTube says, do you have any suggestions for online resources for independent study? I have nothing but free time until I ship to Navy basic training in February.
CosmicQuest.org.
Quest.org, of course.
We have a bunch of citizen science projects going that we're looking for human beings to help us map out the surfaces of Vesta and the moon. We periodically run classes. We have seminars. We have very active forums that include the Bad Astronomy and Universe Today populations.
Mhm. But
There's all sorts of ways to get engaged.
right, so there's ways to get engaged, but I think I think the question here is independent study. Now, I mean, you could always go back through our back catalog of 276 episodes of
Yeah.
Astronomy Cast, because we've essentially, if you can power through all of those episodes, you'll walk away with a very thorough understanding of space and astronomy at a certain level, right? Is the key. So, but what if a person wants to take things to the next level and wants, either not accredited but wants to study better? I mean, there's an advertisement
Yes.
at the beginning of every episode of Astronomy Cast, right?
Right. So, well, that's actually accredited. So,
Swinburne, yeah, and that's
if
accredited, right?
yeah, so if you want to get an accredited degree in astronomy or take some classes, Swinburne Astronomy Online out of Australia, they do a lot of project-based astronomy learning. So you're doing independent research. You're working with astronomers all around the world, and so that's a really neat program. And there's all sorts of astronomy content. Just spend time on Google Plus. There's a huge community with the SETI Institute is doing regular lectures now.
Hmm.
All sorts of different ways to get engaged.
And there's some pretty neat stuff happening in online learning. Like there's Udacity. I don't know if you've been to Udacity's site.
No, not yet.
Yeah, just a phenomenal educational resource, mostly for computer science, though. So
Okay.
they're starting to add some other stuff, but I'm sure within the next couple of years there will be astronomy material there as well, and it's really great. I mean, you can get a full-on computer science degree through Udacity, and then it's all
That's
free
cool.
unless you want to take the tests, and then you have to pay for the test, but then you can get accreditation. So it's quite impressive. So somebody, Steve wants to know, how is Uwingu going?
Oh, so the reason that I look so sleepy is because I've been programming my butt off. The team of us here in Edwardsville spent our entire weekend working with Alan Stern and Cindy Conrad, planning out what needs to get done to get to launch. And as soon as we're done with this, I'm going to be trying to get the last bits together so that we can have internal beta testing. And so it's like this close, but we're on that last 10% that makes you want to gouge your eyes out.
Um, let's see. Thomas Traniker wants to know, is it possible to have a black hole without spin?
Theoretically, yes. Reality, it's a real expletive to form something with zero angular momentum.
So you've got this situation where the black hole will likely have the same angular momentum as the object had before it became a black hole, right? If
And
it
it
was
gains
turning.
angular momentum from stuff falling into it. So yeah, the trick is how do you get something not rotating in space, and you don't.
At the same time, though, there's no possible way to actually measure the spin of the black hole because it's all hiding behind
Um,
behind the event horizon,
there's
right?
so you can't measure the direct spin of the black hole, but you can get information. So how the black hole spinning affects the short short
Schwarzschild radius, yeah.
yes, it
Yeah.
affects the shape of the
Right. Isn't this concept of the naked singularity, right?
yeah.
You have a situation where the black hole can actually I'm trying to remember. I may mangle this, right? But that if it's rotating so rapidly, the black hole may actually extend outside of the Schwarzschild radius that you can
It's
actually,
all yeah. So
yeah.
spin. shapes the geometry around the black hole. And so you can get all the calculations that you do in undergraduate, and in fact in many graduate classes in astrophysics, all assume zero spin black hole because, well, that's solvable easily without too many tears. But as you start looking at spin, looking at the influence of spin, you realize there are detectable side effects. There's been some really neat press releases in the past few years about this. But the math also becomes much more difficult because you do have all these neat geometric properties. And yeah, so it's cool work, and it's awesome that you can get hints of what's going on within the event horizon. But you can't actually look inside the event horizon and go, oh, it's rotating once every 200 seconds.
Right, right. There is no way to actually measure the spin.
Yeah.
Because
you can just measure effects that
could
relate
be, yeah,
to known properties of spin.
I wonder, though, once the, if gravitational waves are, the detectors get really good and they're able to measure gravitational waves coming off of objects, I wonder if the spin of the black hole will somehow be detectable by the through the gravitational waves that are generated as it consumes material, As,
I just don't know.
Yeah, I don't know either.
That's not part of any of the models that I've seen, but that doesn't mean
Nobel
I just
Prize,
haven't seen the right
please.
ones.
I want my Nobel Prize, please.
You can't get a Nobel Prize till they detect what you predict.
Right. Okay. Well, I just predicted it, so it's
don't
now recorded on YouTube. I've just predicted measuring the spin rate of black holes through gravitational waves. So that should be made more complex. So sorry, Greek person 0305. It's CosmoQuest, so .org.
Yeah,
it's not
COS.
Cosmic Quest. Yeah.
Let me. I'll change my lower third.
CosmoQuest.
I was lazy and just put my Twitter handle today.
Well, that's a tough one to spell. So that's why.
That's why it was still available when I bought the URL. Trying to find new URLs is a constant challenge nowadays. And I managed to misspell it again.
Nice.
Yeah,
so
it's
don't listen to what Pamela says. So has anyone else got a question? I think we kind of run through the questions. Actually, so one other last piece of information, which is that if you want to get a notification that we're going to be recording Astronomy Cast, the best way to do that is to actually circle Astronomy Cast page on Google+. And so what'll happen is you'll circle Astronomy Cast, and Astronomy Cast will circle you back. And then when we post the event for each recording that we do, we'll invite you to the recording. And then you'll know that we're actually going to be recording, and it goes right into your calendar, and then you can't miss it. Okay, well, I think we're done. We've got all our questions answered. It was sort of a quiet. We kind of sprung this on people, so we didn't get as many questions. So, well, thank you very much, Pamela, for taking the time as always, and thanks to everybody who watched. And next up, like I said, we're going to probably do another episode in the next couple of days. We'll negotiate a time that works for both of us, and we'll do today's episode in a couple of days. So we're ready for next Monday's episode. And then also we've got the Weekly Science Hour on Wednesdays. I'm not sure what's happening this week.
I think it's you and Emily.
Is it me and Emily? We're going to talk about them. Good. That's always really fun. We talk about the Curiosity rover, and Emily is again an absolute bottomless fount of knowledge about the rover. Yeah. She can planetary science circles around all of us. So. And then Thursday we're going to try and get the Weekly Space Hangout rolling. We've had sort of, it's ironic. There's been so many big news stories coming out, and everyone's been so busy, and there's been so many press conferences from NASA and stuff that we have a really hard time getting the masses together. So
we're going to try again this week. I'm not traveling this week, so that's
good. All right. Well, then I will throw a whole bunch of stories just at you. Okay, cool. All right. Well, thanks again, Pamela. Thanks everyone watching, and we will see you all next time.
Sounds great. Talk to you later.